Today I will show you how to clean up a final image which has some artifact in the point sources. So we can see this point source has some spike sticking out of it, and so does this one, so does this one. So it's some systematic problem in the entire reduction, which seems to be affecting the entire final image and all the point sources in it. So what we must do is go back and reprocess the entire set and look at each individual orbit image to try to determine where the source of the problem is. Perhaps an artifact like this is caused by drift correction, poor drift correction, for example, or it may be caused by some other issue, but obviously there's some issue there. If you don't have contrast scaling on, you won't see it because the main point source is so strong, but you can kind of see it if you look closely here, and if you creep up, you can see it. If you match contrast, then it's definitely clear that there is something wrong with the drift series correction, the drift tracking, and the correction. So let's reprocess this field from scratch. So it's this file right here. I'm ready to go. So just hit enter. Okay, so we see in this drift series that there are in fact a very large number of sources which are very strong. And although it's going very fast here, we can certainly see that really decent tracking is actually happening just because there's so many sources there. Now you could go through this manually and see if there's a problem with drift series. For example, if you only have one or two sources, it should warn you in that case that there's a problem with drift tracking. But in this case, there's no problem with drift tracking whatsoever. These are all very good tracks because there's so many sources, and so they're going to average together quite well. Yet we still have a problem after the reduction, which we will see in a moment. Okay, so these are the unregistered files. As you can see that there's going to be some movement. But if we flip through them, here's one right here. So this is actually a calcium fluoride image. The final image we were looking at previously was actually a sapphire image. So we see that there's actually a problem in the calcium fluoride filters. You can see that that's a double, right? Something has happened. And this is unknown why this occurs. I'm not sure if the mirror is loose or something and there's just a slight offset that happens sometimes when the telescope moves just right to cause a slight differential, because you can see that it was pointing, what was happening is that the telescope was obviously pointing here mostly, but then there was some step function offset which caused the rest of the counts to come over here, right? And that's consistent with all of the point sources. And so this isn't a drift series problem because the drift series was actually excellent. All the drift series were good. You can just tell because there were so many sources in those drift series. So why this problem still happens, it's actually unknown. Just speculating. It's some sort of offset that sometimes, it's infrequent, it's quite rare, but sometimes some step function offset happens between the pointing of the Viz telescope and the pointing of the FUV telescope, which causes this differential. This is rare, but it does come up from time to time. But this is what causes that streak, because actually what would have happened is that drift optimization would have been performed, but drift optimization happens on a 9x9 window. And so on that 9x9 window with this source just outside that window, that's what turned it into that spike that we saw. What we can do first is let's just register these images so that they're lying on top of each other. Okay, now let's scan through these to make sure the alignment is good. Yeah, so you can see that there is some rotation there. And we want good leverage to be able to determine this rotation. So let's use that coordinate over there. And this coordinate here, that gives good leverage across the entire field. So if you just use these 2 points, it's very hard to accurately determine the rotation between those 2 points when the field rotates because there's very little distance between them, very little leverage. However, this point and this point are across almost the entire field, and so that gives you good leverage and therefore good accuracy on the rotation to derotate it. Okay, so just make that box big enough. Right click, should I use the mark coordinates? Yes. Run through automatically? Yes. Now, one thing maybe I should have pointed out at the beginning is if you are not using a high performance system, if you're say on a laptop or something, change your machine performance to standard. I have a very extreme system myself, but if you're just on a laptop or something, or an older desktop, just use standard machine performance. Okay, so let's scan through these. So now we can see as we scan through there is no rotation. They're all lined up. But we do see for this one calcium fluoride image, this doubling problem here, this offset. So how do we correct that? We correct that using drift optimization. So we just want to focus in this window, make this window as big as it needs to be so that it's just capturing plus a bit of the wings, the single source that's been split into two. So that's a good size right there. So now we go UVIT, create drift correction list, PC mode, drift optimization or optimize point source ROI. So now we want to check off auto detect, check off auto optimize. So that means that it is now with those unchecked, it is going to use the window region of interest that you have specified here, but it can't do auto optimization in this case. So you just have to specify a time. So just specify something like 10 seconds will probably be sufficient. Okay, so what we want to do is we want to select out this image only from the set. So just press this finger button and that makes this image be singular in the list because we only want to correct this image. So now we go to UVIT, create drift correction list, PC mode, optimize point source ROI, and now we leave that at 10 seconds and now just double click this. And now we see that it's been corrected. Like magic. Very nice, right? That double source is now gone. So now what we can do is, just because there would have been some movement, because there was some offset there, right? There was that double, that single source was split into a double. And so now because of that correction, it may have deregistered it slightly from the previous registration that we performed. So let's just re-register the entire set. So it'll go through and it'll pick out the most recent file. So now it will ignore the previous image here that had the split, and it will use only this updated one, which has been corrected. It'll do that automatically. So press OK, and let's just use this single brightest source. Right click and run through. Yes, we can automatically run through. Okay, now let's scan through. So I'm scanning pretty fast, but you can go slower if you like. I'm used to doing it very quickly, so half-second cadence if you like. In any case, I'll go down to 0.1 seconds. And so this all looks very good. There's no rotation. This point is staying on top of itself over the entire range of images. You can see variations in noise and background count due to variations in the total exposure time for each orbit. Okay, so these are looking very good now. So now we can just proceed as usual with merge. Okay, so here are the merged images, and now we see that there is no strange artifact in the final images. Nothing in the calcium fluoride or sapphire or barium. These look good. What we do want to do, just to finish up with you, let's do drift optimization. So set a nice range. It's usually helpful to set this elliptical region of interest because if you don't, it really likes sources that are on the edge, but sources on the edge go in and out of the field, and so they'll totally destroy the optimization. You want to make sure you're only getting sources within the field window, within the active part, not near the edge. Okay, so that's good. Now, if we just want to see if this actually improves things. So for image 1, we're at about 1.3 arc seconds. Image 2, again, about 1.3. Image 3, this is Sapphire, 1.4 arc seconds. So let's see if auto drift optimization improves these. So now we're going to go auto detect sources. 75 is probably too many. It doesn't look like there's that many sources in this field, so maybe 30 would probably be a good, just rough estimate to use. Okay, double click that. And yes, we want to do it on all. So it sets this window automatically to 9 by 9. It automatically finds sources to use for the optimization. Okay, that's done. Now it's on the same source. Has it moved? So here's image 1. Now we have 1.2. So yeah, there's been an improvement. 1.16 arc seconds. And here's Sapphire, that was 1.4 before, now it's 1.28. So improvement in the PSF for all of the images. So of course, if you just want to go through it together, the last thing to do would be you have to download the new catalog for this area and just put it inside the observation ID directory. So there's the file, there's the catalog. This is Gaia DR3 downloaded. So we'll put that file automatically here, and then we just press solve. There we go, solution right away. Clear solution points, sure. So we solved that on barium fluoride. And just check the solution here. Look at that, very good. Standard deviation of WCS residuals is only 0.12 arc seconds. So that's the error of the world coordinate solution fit, 0.1 arc seconds. Very nice. So now we would just proceed as usual. Derotate, yes. Okay, and then finalize. Okay, excellent. So I hope that helps in case anybody runs into an image artifact problem like that where a point source doesn't look right. This hopefully gives you a tool to try to fix it yourself. Otherwise, you can always just contact me, jpostma at ucalgary.ca or joepostma at live.ca for help with your reduction. Take care. Bye.